Good morning. Today's lecture will be on fixed-to-fix models. This is the third lecture of the Quant 3 course. So as a quick overview, the following two lectures will cover methods of identifying causal relationships when you have panel data. And with panel data, I mean data when you have repeat observations across time for the same individuals or the same units that you're examining in the data. For example, you might have repeat observations of health outcomes for the same individuals, and it might be before and after the expansion of healthcare, or you might have data on employment rates over time in states, and you also have data before and after changing the minimum wage laws in a state. So when you have panel data, there are many opportunities to distill causal relationships. I will be discussing two of those, fixed-to-fix and difference models. These two models have a very similar intuition in how they uncover causal relationships, because they both look at the changes over time. And by looking at the changes over time, you're able to get rid of most of the sources, not all of the sources, of emitted variable bias. I will then show you that these are actually more or less the same thing, fixed-to-fix and difference. It just depends on the policy question you are examining and the data that you have available to examine it. Often difference models are the estimating equations in order to do a difference model often relies on fixed-to-fix. Right, so let's just start with a very simple example to build the intuition for fixed-to-fix. Let's say you want to estimate the impact of the number of police in a city on the crime rate. And now what is very important here is that we have the subscript IT. I refers to the city I and T refers to the period T. And we have panel data because we have multiple observations for the same city. We have, for example, crime rates in 1995, 1996, 1997, etc. And we're looking at the number of police in T-1. So we want to, for example, look at the crime rate in 1996 when, depending on the number of police in 1995, one period before that. Now, if you want to look at the relationship between number of police and crime, you are dealing with the endogenous model here. The error term could be correlated with police. Why? Well, if you can think of some kind of sources of emitted variable bias, you might just have kind of low economic opportunities driving both having high crime rates and more number of police. Or there could be just some kind of historical factors that are kind of causing both of that, or maybe more crime is actually causing more police, the other way around. And so here we can just show you this spurious positive correlation. This all comes from the textbook, where you just look, this is now all the data you have, and you plot this relationship between robberies, the crime rates on the y-axis and police on the x-axis, and you see this positive relationship. But you will see if you break this down for every single city in the data, within every city, there's actually a negative relationship. Fresno, for example, has both low numbers of police and low crime rates, but in years when it had far fewer police, it had much higher crime rates. The same for other cities. San Francisco has both high numbers of robberies and a high crime rate, but there is this negative relationship within San Francisco. And this is the key intuition of a fixed-to-fix model, as you look at this relationship between the dependent and the independent variable within the same unit. Within a city, is there a negative relationship between crime and police? Right, let's show you the actual model of fixed-to-fix. And so the only difference really that you see here in the estimating equation is that the error term, now that is, remember, epsilon, contains some information that is fixed, which is constant for that city, and some information that varies over time. And so this can be broken down into this time invariant characteristics. That Greek letter is alpha, denoted with only an I, denoted only with an I because it does not vary by time. It is a different value for every single city, but it's everything that does not vary over time. And this other component, and this is called upsilon, not epsilon, which does vary over time. And so you substitute in these two components of the error term. And what this alpha I actually represents in practice in this model is a different value for every single unit. And so this would, in this case, be the average crime rate over time for every single city. So it is the average crime rate for every single city across all the different time periods. And the other error term is just this, this changes over time of the crime rate. So what you actually want to do is, when you estimate this model, is you actually throw in a dummy variable for every single value of I. So, for example, if you have 4 cities in your model, and the 4 cities are Fresno, San Francisco, Palo Alto, and you just throw in a different dummy variable. So one dummy variable is equal to 1 if it's Fresno, another dummy variable is equal to 1 if it's Palo Alto. I might not even be making up correct cities, and another dummy variable is equal to 1 if it's San Francisco. Now, the same way we were thinking about categorical variables is if there are n different cities, you can only throw in n minus 1 different dummies. You always leave out one city because that's captured, that city's average is actually captured by this constant term beta 0. So let's look at this in practice. This is a kind of stylized example. These 3 different cities, thinking these are actual city names. And let's just say you have 2 different time periods for every single city. And then this dummy variable is equal to 1 at D1 if it's Fresno, D2 is equal to 1 if it's Oakland, and D3 is equal to 1 if it is San Francisco. And then you throw in a dummy D1 and D2. You can't throw in a dummy D3 because of perfect multicollinearity, it will just fall out. But you just throw in a bunch of dummy variables for every single city. And I will show you in person how to actually do this in practice in Stata. But even though you throw in these dummy variables, when you actually show this as an estimating equation, it's actually just shown always like this, just representing the fact that you will be controlling for all of the time invariant characteristics in that city, and how, in the sense of how it relates to crime. Right, but there's another way to think about fixed effects models that are actually very intuitive, and this is called the d-meaned approach. And it's quite beautiful. We can show it mathematically, but you can also write that same equation in terms of deviations from the mean. Thinking about this on the left-hand side here, y bar I means for an individual city I, the average crime rate. So here, for example, individual city Fresno, the average number of robberies is just the average of these 2 values, more or less 7.2.5. And so you just subtract in that time period that very specific value of the number of robberies by the mean, the average in that city. And you do the same for the number of police. You take the average number of police across time in that very specific city and subtract it from the actual number of police in that specific time period. And so you can think about it like, what is the relationship between a change from the average with the and with the relationship with the change in the average of the dependent variable? And it's beautiful. It's exactly the same thing, but it's a better intuition as you're looking at the change in X and how that determines or is related to the change in Y. And the idea here is that it subtracts all time invariant characteristics. So why is this important? If it captures all time invariant characteristics, it basically takes away everything, even though you can't control for some very weird thing that's going on in the city. The fact that you are subtracting out the mean is that you're controlling for all characteristics that are not varying over time, even though you do not have the data for that. So all of the sources of omitted variable bias for characteristics that do not vary over time, you just get rid of, even though you can't even control for it. Just by controlling for every single unit, every city separately, you're controlling for all of these factors that could be driving the results, but only those that do not vary over time. So it subtracts out all the time invariant characteristics. And it only looks at the variation. So you always think about this in multivariate regressions. What is the variation remaining in Y after controlling for all these other factors? It only captures a variation within units, within the city, because these fixed effects that you've thrown in, these dummy variables, are controlling for all of the differences between units. So you're looking at fixed effects model, looks at variation within units rather than between units. Now, what's very important is actually if you want to control for some other time invariant characteristics, let's say you want to control for the year that the city was started, or you want to control for its population in 1960 or something, any kind of characteristics, or whether distance from the ocean, any other characteristic that does not vary over time, if you try and throw in the model, it'll just be dropped out because of perfect multicollinearity, because all of these time invariant characteristics are already controlled for by throwing these dummy variables, controlling for every single city separately. So I just want to show you visually this intuition of a fixed effects model relating to deviations from the mean. And so this is the own data that I constructed. We will be playing with this when we meet in person. And so there is this, again, this positive relationship between number of police and number of robberies, which is crime. But we had 3 different cities, and I took 3 cities in South Africa, Cape Town, Johannesburg, and Bethlehem, which is actually a South African city where my mother was born. And we have a situation where Johannesburg has both high number of robberies and many police. Cape Town is intermediate and Bethlehem is low. But really what's driving this positive relationship we observed is actually the fact that some cities have both high levels of crime and number of police. But within each city, there's this negative relationship. And this is, again, also the kind of intuition of omitted variable bias, right? Positive relationship, which is hiding a negative relationship for every single value, and this value of, for every single city. Right, so what do you actually do when you take the mean and you look at the deviations from the mean? Well, let's think about it like this. Look at the mean value of X and Y for every single city. So this is this point where these dotted lines meet each other. That is now that will be the new center. That will be 0.0 if you subtract the mean both from X and from Y. And you do the same for this city, and you do the same for this city. You do it for every single city. Now you actually stack them on top of each other. You stack them at that point when they have the mean value of police and the mean value of crime. So you're actually moving all of this data sets, kind of squashing them together. And this is remaining variation that you're actually looking at when you have a fixed effects model. And of course, now you actually have this negative relationship that you're capturing. Great, that's it for this. Oh, one more thing, sorry. a kind of addition to the fixed-effects model, a kind of version 2.0, is what they call a two-way fixed effects model. This is a very important term to know and understand. And what it actually does is we have now control for the average crime in every single city, looking at these in city-specific fixed effects, but there are also trends over time. You know, maybe crime is rising over time, or there was a spike in one specific year where there was a very high crime rate. This could create its own sources of bias, right? Because we know that some things just co-vary over time for a bunch of like third factors that could be driving it. You know, the number of police is increasing over time because of, you know, cultural factors, the 1960s liberalism or something that is kind of across the whole country that's driving both crime and number of police. Just another example, you know, if you want to look at the impact of cell phone coverage on GDP, both of these variables have been increasing over time, but if we don't control for this time trend, we will just be estimating this spurious positive relationship. And so what you can do here is now we have this other part of the error term. We had alpha before and upsilon. Alpha only has a subscript I because it only varies by the city level, not over time. It has one value of y for every single city. And it's in effect, this value is just the average value of y across all time. But now we have this other component of the error term called tau, and tau only varies over time, and it does not vary across cities. And this is basically the average crime rate every single year across all of the cities, right? So now you're averaging across cities to get the average for every single year, where alpha I is averaging across time to get the average for every single city. And again, you estimate this by just throwing in a dummy variable for every single year. So now this model would have a dummy variable for every single city and a dummy variable for every single year. It's harder to represent this visually, but the same intuition applies. This does not solve all of our problems, unfortunately. And this is important to understand. And this is unfortunately going to be a very common theme across all of our lectures, is that every single quasi-experimental method, it wants to mimic an experiment, has its shortcomings and pitfalls. And in this case, there might still be endogeneity, because what we're doing is we're controlling for all of the time invariant characteristics, or the set fixed characteristics of a city. But actually, most of the characteristics we have control for time invariant characteristics. But especially with a city, most of the characteristics vary over time, right? So you have all these factors that are also changing over time, right? Economic conditions are changing over time. Population is changing over time. Education rates are changing over time. All of these things are in effect time invariant characteristics. And all of these factors could be sources of admitted variable bias. We could have a situation where during economic hardships, crime goes up and investing in police goes down. So it's really economic hardship. So we just have a situation that every single time period where things are going badly, we also have a situation where at the same time, there's more crime and fewer police. And you can think of all these other time invariant characteristics that might be driving crime. You know, population increases, for example. And there's this other thing, which I won't go into detail, but fixed effects, it pulls out a lot of the variation, right? But sometimes it can get rid of both the good and the bad variation. And sometimes all the variation that's left is just noise, because there's always measurement error. And then you're creating, you have your kind of cause, whatever, your solution is greater than the problem you had in the first place, especially if you have a measurement error. It becomes quite a problem if you have measurement error. And most importantly, we have this omitted variables that could driving a change in X that also explain a change in Y. So it's really about these factors that are changing over time that could be a source of omitted variable bias. Right. So to conclude today's lecture on fix-to-fix, we've demonstrated how with panel data with repeat observations across time for the same unit, a fix-to-fix model could be a very powerful way of dealing with omitted variable bias because it controls for all time invariant characteristics, both observed and unobserved. Gets rid of all time invariant characteristics by just controlling for the fixed unit itself. And the key intuition is that it looks at variation within units, say within a city, rather than variation across units. It's commonly represented in a two-way fix-to-fix model, where you include controls for both the units themselves, the cities, and also the time periods, which controls for any time trends that might be in the data. But it has its own shortcomings because there might still be omitted variable bias in time varying characteristics, i.e. a third omitted variable causing both a change in X and change in Y. That's it for now. In class, we will be playing around with data to get a better feel for the intuition of how this model works. Thank you.